In this video, we're going to be solving the integral from 0 to 1 plus 1 over 1 plus 1 over dot 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 of square root of tangent to the sixth of 1 minus x over square root tangent to the sixth of 1 minus x and on and on and on dx. So first, let's focus on the upper limit of integration since that's not in a ready form. So we're going to have to convert it into a definite form. So first, we start off by writing in setting equal to y. And notice that we have 1 plus 1 over dot 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 in the denominator of that, but y is also equal to 1 plus 1 over dot dot dot. So we can just say, replace the denominator with y and say that 1 plus 1 over y is equal to y. Multiplying by y on both sides, we get y plus 1 is equal to y squared. Solving this quadratic, setting the one side equal to 0, you get y squared minus y minus 1 equals 0. Implementing the completing the square method, we take -1, divide that by 2, so you get -1/2. -1/2, you square that value, so you get +1/4. So decompose the -1 into +1/4 and -5/4. Now factor the y squared minus y plus 1/4 into y minus 1/2 whole squared, and then the -5/4 and the equals 0 stay the same. Now add 5/4 to both sides to get y minus 1/2 whole squared is equal to 5/4. Now take the plus or minus square root of both sides to get y minus 1/2 is equal to plus or minus square root 5 over square root 4, which is equal to plus or minus square root 5 over 2. Now add 1/2 to both sides, so you get y equals 1/2 plus or minus square root 5 over 2. But here, as you can see, we have two solutions, the plus or minus. But notice that y is defined as 1 plus 1 over 1 plus dot dot dot. The only number involved is 1. So we can only know that it's positive. So we only take the positive solution, 1/2 plus square root 5 over 2. And this is equal to, we can merge the denominators because they have the same denominator, 1 plus square root 5 over 2. So the upper limit of integration is going to be 1 plus square root 5 over 2. So this is equal to the integral from 0 to 1 plus square root 5 over 2 of that square root tangent to the sixth of 1 minus x. Now I should note that 1 plus square root 5 over 2 is actually equal to phi, the golden ratio. Phi is a Greek symbol, just to notate that. So I'm going to be replacing the 1 plus square root 5 over 2 with that phi symbol. Basically means the same thing, it's just a shorthand term. Now we're going to simplify the integrand. So square root of tangent to the sixth of 1 minus x over square root tangent to the sixth of 1 minus x dot dot dot. So first let's rewrite it to see what's happening. Alright, so as you can see, tangent to the sixth of 1 minus x keeps appearing. So let's make a u substitution by letting u equal tangent to the sixth of 1 minus x. This will simplify things a bit. So we get, implementing that into this, we get square root of u over square root u over square root u dot dot dot. So this is equal to, the u on the top only has one square root applied to it, so it's going to have u to the power of 1/2. The u on the bottom, the u below it is going to have two square roots applied to it. That's going to be u to the 1/2 times 1/2, which is going to be u to the 1/4. And then down you go, you multiply by 1/2. So u to the 1/8, u to the 1 over 16, and u to the 1 over 32, and so on. So how can we get this into a definite value? Well, we can start by converting the denominator into positive and negative exponents. So we leave the u to the 1/2 on the top, and then we have the u to the 1/4. The u to the 1/8 is actually the denominator, so we can bring it up to make it in the numerator of the denominator. So it's going to be u to the -1/8, now u to the 16th, and then u to the -1 over 32. And it keeps on going. The signs change. So now we can bring all of those up by changing the sign of them, the exponents. So the u to the 1/4 becomes u to the -1/4. So overall, you get u to the 1/2 times u to the -1/4 times u to the 1/8 times u to the -1/16 times dot dot dot. Now, by the laws of exponents, we can add the exponents together. So we get u to the 1/2 minus 1/4 plus 1/8 minus 1/16 plus minus dot dot dot. So now we have to solve what that exponent is, because we still have an infinite series. Let's see what this exponent comes out to. So we have this infinite series, and notice that this is a geometric series. So first we take the first term, which is 1/2, Now we have to find the common ratio. The first term and the common ratio are the two things needed to find the sum of an infinite series. Here we notice that the common ratio is -1/2 because you always have to multiply the first term by the -1/2 to get to the next term. So we plug in those values into the formula a sub 1 over 1 minus r. So our first value was 1/2. We get 1/2 over 1 minus -1/2. 1/2 over, that's going to be the same thing as 1 plus 1/2. Then you simply get 1/2 over 3/2. 1 plus 1/2 is going to be 3/2. And multiply both by 2 and you get 1/3. So that in the end is equal to u to the 1/3. But recall what u was. U was actually tangent to the 6th of 1 minus x. So that whole infinite square root thing with the tangent to the 6th of 1 minus x is actually going to be u to the 1/3, or tangent to the 6th of 1 minus x to the 1/3. So we multiply those exponents together, 6 times 1/3, to get 2. So we get tangent squared of 1 minus x. That's because we're taking the cube root of tangent to the 6th of 1 minus x. And this is our final integrand. So let's put that into our transformed integral. Tangent squared of 1 minus x dx. Now we simply have to solve this integral to get our answer. Okay, so first look that we have a 1 minus x there. We want to get rid of that. So let u equal 1 minus x such that du is equal to negative dx. We have a dx, but we don't have a negative dx, so multiply -1 in the inside, but also the outside to remain equal. Now we have the negative integral. Now you have to change the bounds. So 0, or u sub 1, the lower limit of integration, turns into 1 minus 0, which is 1. And then the upper bound, u sub 2, is equal to 1 minus phi. 1 minus phi in the top for the upper limit. And then we get tangent squared of 1 minus x turns to tangent squared of u. And the negative dx turns into du. Now we have a negative and then the integral bounds. So we can actually swap the integral bounds and absorb that negative away. And it actually makes sense in this context since 1 minus phi is actually less than 1. And recall that tangent squared of u is actually equal to secant squared of u minus 1 by the Pythagorean identity. So integrating secant squared of u minus 1, we actually get tangent u minus u. Let's evaluate it at the bounds 1 and 1 minus phi. So in the end, we evaluated at 1, tangent 1 minus 1, and then subtract, and then evaluate this at 1 minus phi. So tangent of 1 minus phi minus 1 minus phi. And this is our answer. So this comes out to around 0.65. And there we go. We solved it.